Section 4.4, the multiplication rule. So previously we had problems that said A or B, and the or turned into addition. Now we're going to have things that say A and B. The and will turn into multiplication. But first, here's an example. Suppose this couple wants to have 3 children. What's the probability that they have all 3 boys? So here's one way to do it. You write out all of the gender combinations. So here is the possibility where they have 3 boys. They could have 2 boys, 2 boys and a girl. But you have to consider it. The girl could be the youngest kid, the girl could be the middle child, or the girl could be the oldest. Likewise over here with 1 boy and 2 girls, the boy could be the first kid, the middle, or the last child. And last, perhaps they have all girls. So find the probability that they have 3 boys. Well, there's only 1 out of the total of 8 possibilities. So that is the long way to do it. The faster way to do it is, if they're going to have 3 boys, that means it's a boy, and then a boy, and then a boy. The chances of being a boy is 1/2. So that means for the first child to be a boy is 1/2, and turns to multiplication, 1/2, and turns to multiplication, here's the third boy. Multiply, you get 1/8. But it's much faster to do this rather than write out all of the combinations. Here's another example. I Googled and it told me that 38.2% of Californians are Latino. Suppose you randomly pick 8 Californians at random. Find the probability all 8 are Latino. So we're going to have 8 in a row this time instead of 3 in a row. And for each one, we want them to be Latino. Well, the chances of that are 38.2% for each. So that means we would have 0.328 times 0.328 for the first person, the second person, the third person, all the way for all 8 people. So if you do that 8 times in a row, you could just abbreviate it by saying it's raised to the 8th, and then put that in the calculator. There's a very small chance all 8 are Latino. So basically the multiplication rule says if events A and B are independent, that means, for example number 2, when you choose the first person, they happen to be Latino. For them to be Latino, does that have any effect on the second person being Latino? If you're randomly choosing people, the answer is no. In the other example with the gender, so just because this first child was a boy, does that have any effect on whether or not the second child will be a boy? No, they don't have any effect. So if they don't have any effect, the multiplication rule just says and turns to multiplication. You just find each probability and multiply. So here's another example. Find the probability 2 people randomly chosen. They were both born on a Monday. So that means you're looking for the probability of a Monday and a Monday. Again, these are independent. Just because one person was born on a Monday, that does not have any effect on the other randomly chosen person. So the chances of a Monday are 1 in 7. The and turns to multiplication. The second Monday is a 1 in 7. So that's 1 out of 49. Now, to stretch your brain a little bit, compare that question with this one. Find the probability that 2 people were born on the same day. And by same day, I mean day of the week, not the exact day, the exact year. I'm just trying to say the same day of the week, but it wouldn't quite fit on the screen. Find the probability 2 people were born on the same day of the week. Isn't that going to be the same as the previous one? The answer is no, because when you go to the first person and you ask them, what day were you born? What day of the week were you born? And they tell you, I was born on a Wednesday. Okay, now Wednesday is locked in. On this question, I locked it in early. And since I locked it in on a Monday, there's only 1 out of 7 on a Monday. When in this question, when I go up to the first person, they can pick whatever day they want. They can tell me it was a Wednesday, they can tell me it was a Thursday, they can say anything they want. Hopefully it'll be the truth. So they say it's a Wednesday. Now I go to the second person. What's the chances they were born on a Wednesday? Well, for that second person, there's 1 in 7 chance they were born on a Wednesday. So this only has 1 fraction involved. For the second person, it's 1 out of 7. Next up, 4% of cell phones are defective. What's the probability that 2 chosen cell phones are both defective? So again, is this a situation where they're independent? So you pick up one cell phone and then find out whether or not it's defective. Just by picking up that one cell phone, does that have an effect on the cell phone that's next to it or the cell phone that's in a different store? No. So that means that we can just multiply. So defective and defective means that we multiply the 0.04, in other words 4%, times 0.04, which turns out to be 0.002, or 0.2%. Okay, so when is it that they are not independent? When is it that you can't just multiply without any further thinking? Well, that's when you take one of the objects out and don't put it back. So for example, if we were talking about the cards, suppose you get 2 cards. So that means you take one out, you're holding that one card in your hand, the dealer then only has 51 cards left. So that then changes the population. So when we're talking about gender, well, when the first child is a boy, that doesn't mean you take boy out of the picture and boy can never be chosen again. But with this card situation, if you take out a king of diamonds and you're holding it, then that person that's dealing the cards, they can't give you a king of diamonds again because you're holding it. So you have changed the population, you've changed the deck. So on to question A. What's the probability of getting 2 kings? So the first one would need to be a king, and there are 4 kings. So that would be 4 out of 52. Then what happens? So 4 out of 52 is for the first one to be a king. Now this is for the second card. So as I said, 1 card has been taken out, so there's only 51 cards that remain. How many kings remain? 3. So now multiply. On the top would be 12. On the bottom, divide by 52 and 51. And when you do, it's 0.005. Small chance for getting 2 kings. All right, what about this? What's the probability of getting a 4 and then a jack? So when you get a 4, there are 4 out of 52 possibilities for that. Then think about the second card. So since 1 card has been taken out of the deck, there's only 51 cards left. So it has to be out of 51. But the second card has to be a jack. And how many jacks are left? There's 4 jacks still left. And then put that in the calculator, you'll get 0.006. That was a fun section.